we learn that the batch system or closed system goes through several stages, which you have the lag phase, the acceleration phase, exponential phase or lock phase, deceleration phase, and eventually you have the dead phase. We also learned that different kind of products can be produced, or perhaps that each stage has one type of product that can be generated, that can be produced. Now, the aspect that we are covering now is to understand little mathematics that's behind the different stages for the batch culture system. I really would like you to listen attentively and also interrupt to ask questions if you realize that you are having difficulties. Now, I asked you to look at this experiment, which you have several flasks and you have different initial nutrient concentration. And the idea is to measure the growth rate in each of these flasks. Based on the data obtained, you can plot the substrate concentrations against the mu, the specific growth rate obtained. You're going to obtain this shape. And if you do curve fitting, you realize that you're going to have your curve fitting will give this scenario, which is exactly the Monod equation. In other words, the Monod equation can be used to explain the relationship between the limiting substrate concentration and the specific growth rate. Please highlight this section in your material or write it down. Highlight it or write it down that the Monod equation can be used to describe the relationship between substrate concentration and specific growth rate. Okay, I hope you've done that by looking at the relationship that exists between substrate concentrations and specific growth rate. Monod can help to work out that, that relationship. Then I told you that above that, you have so much useful information that can be derived from this model. And during our last lecture, a question was put to you that this graph is not a microbial growth curve. Listen, everybody, don't make a mistake. I can assure you, I'm going to give you the same thing in your exam. Don't make a mistake. This graph is not the microbial growth curve, but it is an illustration of the substrate concentration, which you have here on the x-axis, and specific growth rate that you have on the y-axis. However, it has some similarities with the microbial growth curve that you have here at the right part of your screen. Now, the question I gave to you last time before we left was for you to tell me what are those similarities. Okay, one question was the region A that you have here in the first graph with the Monod equation. Does it correspond to one, the acceleration phase, which is stage 2 on this graph, or does it correspond to the exponential phase, which is stage 3 on the microbial growth curve, or which stage does it correspond? I want to believe that even though we worked it out last time and I gave you the answer, that you were able to digest it and you still remember it.
Maybe 10 to 2.
Sisi, which phase does it correspond? A that you have here correspond to which of the stages of the microbial growth curve does it correspond to?
Acceleration phase.
Acceleration phase is who else has another answer?
Deceleration phase.
Yes, I'll go with Nolu on this aspect that A corresponds to deceleration phase. Thank you for that, Nolu. The idea here is if you compare that on this axis, I'm referring to the x-axis, we have substrate concentration. And by definition, by definition, deceleration phase is a phase whereby cells are facing nutrient depletion. That is, they are running out of nutrients, and the growth rate is not maximal. You clearly see that in the A zone, the growth rate, if you project to the curve and the x-axis, the growth rate here, on the y-axis, the growth rate here is not maximum, it's below mu max, simply because the nutrient concentration is not enough. And again, if you look at the x-axis, you realize that you have lower concentration of nutrient. That's the reason why Nolu has said that the A will actually correspond to the deceleration phase when cells are running out of nutrient. Now, in the same vein, B, from the graph in your left, which stage does it correspond to the microbial growth curve?
Exponential phase.
Exactly. It corresponds to exponential phase because cells have enough substrate. If you look at it, it is the highest region of your S substrate. Secondly, further increment in the substrate here doesn't change the cell growth because they've already reached the mu max, the maximum growth rate. If you project it back to the axis of mu, the value obtained should be your mu max, which is referred to maximum specific growth rate. Okay, your mu max here is called the maximum specific growth rate, and that corresponds to the B region here. And that's where cells are growing at the mu max. That is, the B regions, like your colleague has said, correspond to the exponential phase of growth and the microbial growth curve. Please don't ever forget that. Have you all understood, or you want me to explain further? Because subsequent slide will make use of that. Have you all understood? Kolile, have you all understood, everybody? What goes in? Why we say that it corresponds to the acceleration phase? What we say, why we say it corresponds to the deceleration phase and the exponential phase? Dineo and Paolo, have you all understood that explanation before we proceed? Paolo, class rep, have you all understood? Sorry? Paola, have you all understood the explanation? Please don't be shy. Feel free to interrupt, ask questions if you're having challenges. Okay? Thank you. Dinio has answered that as well. Who else who is having trouble understanding this kind of matching of similarities between the two graphs? Nondu Miso, have you understood? Unmute yourself. Feel free. Don't be shy in this class. Okay. Teresa, have you understood the explanations, the matching of similarities between the graph in your left and the other one by your right? Which section corresponds to deceleration phase? Have you understood that, Teresa?
Yes, I have.
Great. Please feel free. I encourage everyone, if you don't understand, just interrupt. I want you to understand the kinetics to the extent whereby when you are doing your honors next year, you can be the one teaching those doing doing this module. Great. Now let's go to the next slide. Now, the next slide tells us something important and something quite interesting. That two microorganisms may have different affinity for the same substrate. Now, before getting there, let me come back here a little bit. Ks is a monode constant. However, it gives us a very useful information because 1/Ks is used to find the affinity of microbe to the substrate. I repeat, one useful information obtained from this monode graph is a Ks value. Can you all work out the Ks value if you have this kind of curve? Ks value is simply by finding half mu max, divide mu max by 2, and project it down to the axis of substrate. That gives your Ks value. I repeat, to obtain Ks value, you found half mu max, that is mu max divided by 2, and you project it to the axis of substrate. That gives you Ks. However, listen everyone. However, Ks is not the affinity, but the reciprocal of Ks, 1 over Ks. How do I want you to easily understand the affinity? I would like you to interpret it this way. If a cell has affinity for something, if a microorganism has affinity, that means it likes it. If it doesn't have affinity, that means it doesn't like it. Okay, you can keep it like that for the meantime. Affinity means it loves it, it likes that nutrient. If it doesn't have affinity, means it doesn't like it. And that's obtained using the reciprocal of Ks, 1 over Ks. Okay, now, if we, based on the slide that you have on the screen right now, the slide says 2 organisms may have different affinity level for the same substrate. Let's take the case of E. coli and S. cerevisiae, two microorganisms. Now, let's assume that, listen everyone, please listen attentively and interrupt if you don't understand. Let's assume that A is a graph obtained when E. coli was growing on glucose. Okay, let's make that kind of assumption that the substrate in question here is our glucose, and A is a graph obtained when E. coli was growing on glucose, whereas B is a graph obtained when Saccharomyces cerevisiae was growing on glucose. Now, if you go by the definition of affinity, which is 1 over Ks, okay, which of these microorganisms has higher affinity for glucose? Here's a question given to you. Bali or Piwe, we want to try. Which of these microorganisms has higher affinity for glucose based on the explanations and based on the formula to find affinity? Who want to try? Okay. Denio has mentioned that S. cerevisiae has higher affinity. Okay, let me repeat a little bit, Denio. B is for S. cerevisiae. And the affinity is not, if you have KSB is here, it is rather the reciprocal 1 over the value. Which one has higher affinity? Obviously, E. coli, right? Is E. coli, because if you work at the reciprocal 1 over KSA, it will be higher than 1 over KSB. Therefore, E. coli has higher affinity compared to the Saccharomyces cerevisiae in this case. Okay, we all agree with that. That in this case, the organism with higher affinity will be E. coli compared to B. Now, let me lower the, let me take an analogy that we can understand better. What you are saying in this case, remember that I said analogy could, I said affinity can be looked at with analogy of like and dislike. In this case, we're saying that E. coli likes glucose more than Saccharomyces cerevisiae, more than the way Saccharomyces cerevisiae likes glucose. That's basically what the information we're deriving from this graph. That's just the starting point, because we have so many useful information which you're going to derive from this kind of graph. Okay. Now let me take another context. The same microorganism. Remember the previous slide, we said 2 organisms may have different affinity for the same substrate. Now, I'm giving you another information. The same microorganism may have different affinity for different substrate. Let me allow you to reflect. The same microorganism may have different affinity for different substrate. Now, let's assume that we have our E. coli, and we have 2 substrates. One is the glucose, one is the lactose. The question which actually asked one of the examinations, one of the assessment was, I gave them similar graph, asked them to tell me which substrate does the microbes has higher affinity. In this case, which substrate? Is it lactose or glucose? We're dealing with E. coli and two separate substrates. Who want to try? We're dealing with the same microorganism, two substrate, and the question is, which of the substrate does the microbes like more? We want to try. I want somebody from the class to try.
I think it's glucose.
Okay, now because you work out the glucose, which is A, substrate A, glucose here is substrate A. If you work out, we realize that 1 over KSA is higher than 1 over KSB. Consequently, in this case, the microorganism loves glucose more than lactose, or it has higher affinity for glucose than compared to lactose. Having got these informations about the affinity, I would like you to take a look at the shape of these two graphs, these two lines. Hello, class. I would like to take a few minutes, just observe these two graphs. And in the same vein, hello, everyone. Have you taken a look at these two shapes? Because I'm going to change the slide, but I'll come back to it. I'll take a look. We're going to go back to something that will come back again to this slide. Let's go back a little bit to the slide, which I asked to find out which region corresponds to the acceleration phase and deceleration phase. Back to this graph again. You agree that A, the region A, corresponds to the deceleration phase. Bali, are we on the same page? Do we all agree with that? That's what you said earlier on. We agree upon that. Are we still on the same page? Hello, class. Uda,
Yes, sir.
Yes, sir.
Yeah, that A corresponds to deceleration phase. Now, let me go back to where our previous slide. We have these two graphs. Between A and B, on which substrate will the cell have a shorter deceleration phase? Here's a question. This is an exam question again. Based on these two graphs, on which substrate will the cell have a shorter deceleration phase? I'm going to give you 1 mark if you get it right, provided you remind me. Dineo is saying that on the first substrate, which is glucose, the cell will show a shorter deceleration phase. Now, on which substrate will the cell have a longer deceleration phase? That's a question to the class. On which substrate will the cell have a longer deceleration phase? Is it glucose or lactose? Okay, Cici is saying that on lactose. I want to believe that, Cici, I want to believe that the rest is a response to my second question, that cells will have a longer deceleration phase if your culture medium is lactose, right? That's what you are saying, I believe so. Am I correct, Cici? Okay, but students have got given the right answers based on our discussion. Now, this is very interesting actually, in the sense that, remember, a question was asked yesterday, is it possible to extend the deceleration phase? Is it possible to make the deceleration phase much more longer? Now, you can see that two separate substrates with the same cells will show different deceleration phase. The duration will be different simply by changing the substrate, right? By using two different substrates. In one case, you have a shorter deceleration phase. In another case, you have a longer deceleration phase. Now, let me ask another interesting question here before we now summarize our observation. Now, with these two media, okay, there's a question. Okay, the question from Denio is the exam context was going to be the reason, the explanation. Of course, you just said that you have to provide the explanation to your answer. You'll justify based on the affinity level. Okay. In the exam context, you use an affinity level to explain why. You have to explain that one has a higher affinity compared to the other one, right? You have to explain that one has a higher affinity compared to the other one. Now, in the same context, beside the deceleration phase, there's also another important message I want to pass to you. Okay, there's another important message. Let's look at these two lines, this graph. On which substrate will the growth rate not be affected even when the substrate concentration is reduced to a lower amount? On which substrate, either A and B, will the growth rate not be much affected even when the substrate remains small, is reduced to a smaller amount? You have two graphs. Look at your x-axis again. Have a look at your x-axis and find out on which substrate will the cell growth rate not be easily impacted when the substrate concentration is being lowered. Okay, that's fine. The relationship, we're going to come back to it on the next slide. We'll go back to the next slide, Susie. Now, the question to the class is on which substrate which will the growth rate not be easily affected even when the substrate is depleted to a lower amount? Didn't has said glucose. I want somebody else to make a contribution. What does Nolu think? On which substrate? Look at your axis of substrate, which is down here. Also look at your mu axis and observe the two graphs. Make a projection from the two graphs to find out on which substrate will the growth rate not easily affected even when you lower the substrate concentration. Okay, Sisi said glucose, then Teresa said glucose as well. Yeah, you are all correct. Okay, let us reason together. Let's reason together for those so that people that did not understand can now understand. Okay. Are you able to see the movement of the mouse pointer on your screen? Class? Are you able to see the movement of the mouse pointer?
Yes, we can, sir.
Great. Now, I'm on the axis of substrate. I'm going to go backward. Going backward means I'm lowering the substrate in the reactor. Let me repeat. The mouse pointer is on the axis of substrate. Then I'm going backward. Going backward means we're lowering the substrate, right? Now we'll be projecting it on the graph and finding the equivalent, the impact of mu. At this stage, where is the mouse pointer? If I project to the B curve, to the axis of mu, is the growth rate, is it still mu max? No. I've moved at this level. I'm going to project on the B curve and project to the axis of mu. Do we still achieve the maximum growth rate when the substrate concentration is within this region? Class, do we still achieve mu max?
No, we don't.
Would be exactly no. At this region, if you project to the B curve and to the mu, realize that we are no longer able to achieve mu max, even though the substrate concentration is still relatively high. We still have high concentration here. Whereas on the A graph, if you project on the A graph, which is glucose, are we able to achieve mu max at this level? Hello class, if you project from here at the same region on the same substrate concentration, if you go to the A graph and project to mu, are you still able to achieve mu max? Yes. You see that at the different concentrations, one substrate gives us mu max, whereas the other one has started showing a reduction in specific growth rate. Now, let's summarize our observation, or perhaps let me explain for the second time so that you will grab it perfectly. Look at my mouse pointer on the substrate axis. If I project on B at this level, you realize that mu is decreasing already when you are having this kind of substrate concentration. Whereas from the same substrate concentration, if you project on the A axis, you realize that mu is not decreasing at all. Consequently, at the same substrate concentration with B, which is a lactose, cells are lowering their growth rate already. Whereas with the same concentration of with glucose as substrate, cells are growing at the maximum growth rate. Now, let's summarize something here, which I'd like you to underline each of those statements. Now, all the answer that you have provided, I'm referring to all the students that provide answer, can be summarized with these theories here, okay? Underline this theory. Let's go through them first. That if a microorganism has high affinity for the limiting substrate, in bracket low Ks, then the growth rate will not be affected until the substrate is reduced to a very low level. In the same group, the deceleration phase of such culture will be very short, right? I would like to underline these two observations. If a microorganism has a very high affinity for the limiting substrate, in bracket low Ks. Why low Ks? Because affinity is 1/Ks, is a reciprocal. The growth rate will not be affected until the substrate is reduced to a very low level. At the same time, the deceleration phase for such culture will be very short. Class rep, are we on the same page, or you need further explanation? Class rep.
Sir, could you please explain why the deceleration phase will be very short beside affinity?
Okay, let's go back to the graph again. Why the deceleration phase will be short when it has high affinity. Let's go back to the graph. Right. This is our graph. Let's take the case of glucose that shows high affinity. Now, keep in mind, we obtain this graph. It is based on this Monod equation that we're able to make this observation. The Monod equation was obtained in the previous slide by plotting the substrate concentration against specific growth rate. Okay, and we have this shape of graph. The shape depends on the type of substrate being used. By plotting the graph of substrate concentrations against specific growth rate, we have this graph. And I said we have a number of important parameters from that graph. One of which was your mu max, another one was your Ks. And based on observation we have here, even if you put aside the Ks, like you have said, right? If you don't use Ks value, let's have a look at this graph. This is our axis of substrate concentration. If you go backward, you realize that as you are going backward with respect to A, we said the substrate, the growth rate will not be affected until substrate is reduced to a lower amount. Of course, if you are going backward, when you are these regions, if you project it here to the A, the growth rate is not affected. If you go backward further, when you at this region, if you project it to the A, you realize the growth rate remains mu max. You continue lowering the substrate concentration up to this region. You project it again to the A, mu max is still not affected. It's only when you begin to reach this level, this low level of substrate concentration, it's only reach this low level of substrate concentration that you realize that the growth rate begins to be impacted, begin to lower, right? That's why we said that the growth rate will not be affected until the substrate concentrations is reduced to a very low amount, right? This acts of substrate, we are going backward and checking the impact on mu, which is specific growth rate. You are realizing that it's only if you go backward until the substrate is almost is very low that the growth rate begins to go to be lowered. Does that provide answer to your question?
Yes, it makes sense looking at the graph.
Okay, great. Now, if you apply the same logic to the B, you realize that as you are going backward from these regions, which correspond to a high substrate concentration, the growth rate begins to be affected. Cells they begin to grow at a very slow rate. They begin to lower their growth rate. Okay, if you are going backward when you are here, you begin to lower their growth rate. However, if I give you this, although I'm using the graph to explain, if I give you as exam questions, first you will have to, in addition to explaining with the graph, use the mathematical computations of KS to support your explanation. Okay, you'll have to use the mathematical computation of your KS to support your explanation, in addition to talking about the graph and the relationship between the graph mu and the substrate concentration as illustrated by the graphs. Now, the summary of what we've covered is here, that if a microbe has a very high affinity for the limiting substrate, low Ks, the growth rate will not be affected. I think we all understand now why, until the substrate is reduced to a very low amount. At the same time, the deceleration phase for such culture will be short. Let me go back to the graph to have a clear picture. If you look at it, the deceleration phase, which is here, if you refer to what to the region mapping with microbial growth curve, the deceleration phase, which is here, is shorter compared to the deceleration phase of the B substrate, which starts somewhere here. Does it make sense? The deceleration phase of A, which starts from here, which is in this region, is shorter compared to the deceleration phase of B, which span along this region. Now, another observation is if a microorganism has a very low affinity for limiting substrate, that is high Ks value. If it has a very low affinity, that means high Ks value, then the growth rate will be affected even when the substrate concentration is still high. And the deceleration phase of such culture will be relatively long. I want to believe that you have all understood. If you haven't understood, please let me know. I'll go back to it to further explain. You know, if you now have a substrate that has low affinity, the reverse phenomenon will be observed. So the reversal will be observed, where the growth rate will be affected even when substrate concentration is still high, and deceleration phase of such culture will be relatively long. Any question at this stage? Do you have any question at this stage? Okay, what I'm going to do, I'm going to release you at this point, then we'll meet again on Monday to continue with the module. But keep in mind that the Tuesday lectures will be in person or face-to-face lecture that will take place in the lecture theater over there. Any question before, any questions, any aspect in the explanation that is not clear to you? Tokozo, is it clear to you? Is there any aspect that you did not understand? Unmute yourself.
No, sir, it's clear. I'm fine.
Great. If there's an aspect that's not clear, please feel free to interrupt. I will go back to it. I would like you to, over the weekend, reflect on what you have covered. I will also upload the video over the weekend. Reflect on what you have covered, so that when we meet next week, I'll begin to some key calculations, you're not going to have too much difficulties. But I can assure you, don't be afraid. I will make sure that the basic formula that we use are very simple so that everybody in the class will understand. I will ensure that everybody understands, except those that are not coming for the virtual or face-to-face lectures. All right, thank you very much, and I wish you a nice weekend.